In the beginning of the 20th century, astronomers noticed that galaxies were moving away from each other, and the further apart they were, the faster they moved.
Physicists theorised this meant that the universe was expanding, and that at some point in the past, it must have been very small, dense and hot. They called this idea the Big Bang.
Then in the 1960s, two astronomers discovered something called the cosmic microwave background radiation, the CMB, a faint glow or temperature that seems to permeate the entire universe.
This further supported the Big Bang because the only way two extremes of the universe could have the same temperature was if they were close enough to each other at some point in the past.
The theory traced the origins of this glow to 380,000 years after the Big Bang, the point where matter started to clump together enough for light to move around freely. But what happened before this, and how did it happen?
Inflation is the best leading theory, or group of leading theories, of how the universe came to be in those early moments of expansion.
Inflation is a prequel to the conventional Big Bang picture. It provides a story that precedes the expansion of the universe, the formation of galaxies. The way in which inflation explains the Bang is in terms of a very surprising feature of physics, I think very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively. Now, those of us who learned about gravity in high school and learned Newton's law of gravity probably think this sounds crazy, because Newton's law of gravity is purely an attractive law of gravity.
Inflation theorised that the universe expanded so fast, faster than the speed of light in that early time, that these fluctuations created ripples in the fabric of space and time.
These fluctuations expanded and formed hills and valleys in the texture of the universe that allowed matter to clump into the matter we see today.
More precisely, inflation predicted that these ripples would leave a very specific signature of light polarisation on the CMB. BICEP 2 stands for the background imaging of cosmic extragalactic polarisation.
A team of observational cosmologists at the South Pole called BICEP 2 observed the CMB at 150 GHz and saw the swirling pattern. But Planck, observing at 353 GHz, ruled out the BICEP 2 findings and showed that the signal is from the Milky Way dust emission. So to resolve the confusion with regards to the beam signal, the two teams cross-correlated their results and the conclusion favored Planck. The final results show that the signal is from dust, but this does not mean we have to rule out the inflationary theory. It just means that we need more accurate models to search for the beam signal. The hunt is still on.